Hey everyone, we're going to do a lesson on investigating properties of circles. So I've got a bunch of properties here. I'm going to go through them just so that you know exactly what it's saying and what to look for it. And then I'll do an example and I'll show you how we use some of these properties. The first one, chords in a circle that are equidistant, which means the same distance from the center of the circle, are equal in length. Chords of equal length are equidistant from the center of the circle, which means if you have the same length here, like you do here and here, then those chords will be the same length. So AB will be the same length as CD. Also, if you have two chords that are the same length, like this one here and this one here, it means that the distance from O to point S is the same distance as O to point T. So that's kind of a property that we need to keep in mind. Second one, a line from the center of a circle that is perpendicular to a chord bisects the chord, which means it splits it in half. A line from the center of a circle to the midpoint of a chord is perpendicular to the chord, so it's going to make 90 degrees. And the right bisector of a chord passes through the center of a circle. So anything that splits a chord right in half will go through the center of the circle and will have a 90 degree. Also, the distance from AB, so this distance, is the same as this distance from B to D. This one will come in handy for some of the examples as well. A line that is perpendicular to the end point of the radius. So here's the end point of the radius, and it's perpendicular, is a tangent to the circle. A line that is perpendicular to the tangent of a circle at the point of tangency, and the circle passes through the center of the circle. So there you have this example where you have a tangent, and the line that hits the tangent and goes into the center of the circle, that makes a 90 degree. Two tangents can be drawn to a circle from a point outside of that circle. These tangents are equal in length. So if you have a point way out here and you draw a line and it's tangent on this side, and you draw a line that's tangent on this side, then the distance from C to A is the same as C to B. And it doesn't matter where that C is, even if you moved it around and you went the other way, they would still be the same distance. Last one here, if a central angle and an inscribed angle, which we learned in the last lesson, are subtended by the same chord, meaning they meet the same chord, just like in this first example, so here and here, the central angle comes from A and B, and so does the inscribed angle. They both hit at A and B. The central angle is twice the inscribed angle. So whatever angle is the inscribed, it's twice, the central angle is twice that. So you can also find that inscribed angle if you know the central angle just by dividing it in half. Equal chords subtend equal central angles and equal inscribed angles. So here's another one. If they have the same angle, their chords are the same length. There and there. And same with this one. See how they both inscribed angles have the same angle, so their chords are the same length. Let's move on to the next page. So we get this next one. It's really similar to the last one. If two angles are inscribed on the same chord and are on the same side of the chord, the angles are equal. So you can see this angle here is the same as this angle. And they meet on the same side of the chord because you could have one coming this way. That angle would not be the same as that, even though they're on the same chord. They have to be on the same side of the chord, okay? An inscribed angle subtended by the diameter is a right angle. So if you have an inscribed angle, like here, where the diameter is the chord, one of the chords, then you're going to have a right angle right here. All right, we're going to use these properties to do the example. So let's look at what we've got. The distance from the circle to point G outside of the circle is 12 feet. The radius of the circle is 10 feet. What is the length of the tangent from point G to the point of tangency? So let's draw it first. And it doesn't have to be perfect. So I'm going to find the center. We have a point outside here that is G. And the distance of that is 12 feet. We also know the radius is 10 feet. What is the length of the tangent from point G? So point G makes a tangent like that. So the point of tangency, which is around here, we'll say is 10 feet. Now, from our properties, I know that because it's a point of tangency and it goes through the radius, that this is a 90-degree angle. So that leaves me to try and find out what is the length of tangency. So they're looking for this length. Now, if you notice, we've got a right triangle here. Where we know, if I can spell, we know the hypotenuse is 12 feet. And we know one of the other sides, or that could be C, one of the other sides is 10 feet. So we need to find B. So I'll just use C squared equals A squared plus B squared. And I'll solve for it. I'll rearrange it to be B squared equals C squared minus A squared. And we'll solve for it. So we've got 12 minus 10. 144 minus 100. And then to get B, we'll square root that. So the square root of 44 is 6.6, which means that this distance here is 6.6 feet. And that's how you use some of those properties to solve the problem. So when you're solving the problems, look for some of those properties and decide which one it kind of looks like and what you can know for sure about these problems. Try the practice questions, and I'll see you guys in the next lesson.